Okay, hello, Mr. Heisinger here. I'm going to talk you through the remaining portion of section 5.2. Today we're going to look at potential energy. Two different forms of PE that we're going to look at is GPE, the potential energy an object has due to gravitational force that's acting. And then we'll look at elastic potential energy, which is the potential energy an object has because of elastic force. And we'll take a look at these problems at the end of today's lesson. Let's go ahead and begin. Okay, so let's go ahead and take a look at a situation where I might be lifting a block off of a table, and I want to determine what happens to the work that I do when I lift that block up. Where does the work go when you lift a block? Let's assume the net work is 0, so I'm doing positive work, gravity is doing negative work as I lift that object up. I'm not changing the kinetic energy, so the net effect of my efforts is to just simply lift it up. I'm not changing its KE. So where does that energy actually go? Because I am expending energy as I lift that thing. It's just that gravity is also doing work, and it happens to be negative work. And that ends up sort of canceling the effect of the work that I did. But we all know if I let go of this thing, it's going to have capacity to do work. If I let go of this block, it's just going to fall down and be able to do work on that table. So we have to talk about the energy that's actually stored in that position. We call that energy gravitational potential energy. Work done against gravity stores energy in the new position. That energy that's stored, which we call the GPE, equals the work done by external forces by moving from one elevation, which we call the reference location, to the final elevation. The equation that we would use for that would be gravitational potential energy is just mgh. This is just the force due to gravity. It's the weight of the object. And this here is how high up I'm lifting it. So this is my distance that that force acts. So work is always force times displacement. In this case, the work is the gravitational force multiplied by the distance that I moved that object. It is a scalar quantity. The units would be joules or Newton meters, and it could be negative. We'll have to look at this a little bit more to understand why it's negative, or it could be negative rather. First, let's intuitively look at that this equation actually makes sense. The bigger the mass of the object, so if that object is quite a bit larger, it's going to have more gravitational potential energy, and that should make sense. If you have a big heavy block above the table, it's going to be able to do more work as it falls down and changes its position. It's going to be able to do more work on that table than if it were a smaller block. So that should make intuitive sense. And also, the higher up I am, if that object is way up here, it's going to be able to do more work on that table. And again, that idea, those two ideas, that the gravitational potential energy depends directly on mass, and it also depends directly on h, should be intuitive. Now we got to look at this reference location and how it could be negative. Why is a reference level needed in order to compute an object's GPE? And really, the reason we need a reference is that GPE really just describes the difference in energy between two locations. It doesn't make sense to describe the GPE at any one spot. Really just a difference in GPE between two locations. So we have to choose a reference location. In this particular example, the reference location is chosen at the top of the table. And so what is the GPE of this object relative to the top of the table? Well, then my h would be from here to there. And so this might be my initial position down at this spot, and this is my final position. So if I wanted to compute the gravitational potential energy here relative to there, it would just be m times g times the difference between these two elevations. Now we could have a negative GPE, and this is how we could do that. Let's say that I choose my reference location to be the ceiling. So way up here is the ceiling. And what I would like is, I'm going to say that that is my reference. I want to compute how much GPE this object has relative to the ceiling. Well, anything below the ceiling would be a negative h value. I'm actually below that position. So if this is my zero energy position, the ceiling, then anything below that would be a negative GPE. And again, how I could describe that by saying what is the difference in energy between these two spots, I would say that if this is my position relative to the ceiling, this has less energy than it would up here, so my GPE at this spot would be negative. And the way that I would compute that, let's just say that this thing turned out to be 1 meter below the ceiling, and it was a 1 kilogram block. its GPE at this spot relative to the ceiling would just be 1 kilogram times 9.8 newtons per kilogram multiplied by a negative 1 meter, and so its GPE would just be a negative 9.8 joules. And that's again describing the energy that the object has at this location compared to the energy it would have here. It's actually got it's got 9.8 joules less potential energy here than it does there. That's why we have a negative. Okay, so here we have 4 different problems that we're going to take a look at, see how we can use the gravitational potential energy equation. So here we have a wrecking ball, has a mass of 125 kilograms. I'd like to know its GPE relative to the ground 5 meters below. So here I have the ground, and that would make sense for me to let this be my reference location. So I'd just like to know how much GPE it has up top relative to this position. Well, it's a fairly straightforward calculation. All I have to do is just take that the gravitational potential energy is just m times g times h. That's 125 kilograms is the mass of that ball. 9.8 newtons per kilogram, that's a value for g with different units than what we're used to, but that's just because I'm dealing with weight here. And then times 5 meters, that's how high up it is relative to the ground. And so it would have about 6,100 joules of energy there. The way to think of that is that if that ball were to just fall down, it would then be able to do work on the ground below, and it would be able to do work equal to its change in GPE. So it actually drops down 6,100 joules of gravitational potential energy is then going to be able to do work on the ground. Over here we have a book shelf that's holding 6 different equal-sized books. Each book has a weight of 17 newtons, and they're located 2.3 meters off the ground. So how much GPE do those books have relative to the ground below? And again, so this is my ground, that's my reference location, and each one of those books has a weight of 17 newtons, and they're all lifted 2.3 meters off of that ground. So how I would do that, I do have to be careful here about making sure I understand the 17 newtons already contains both the m and the g. So I have 6 books, each one has a weight of 17 newtons, and they're each 2.3 meters off the ground. So I would just go through and say the total weight of all those books is this right here, 6 times 17 newtons. And then each one of those, or all of those, are located 2.3 meters off the ground, so the total amount of GPE would be about 230 joules. I'm going to go ahead and take a look at this one down here now. Take those same 6 books, and this time stack them on a tabletop like so. How much work was done in placing them in this position? Assume each was on the tabletop to begin with, and each is 4.5 centimeters thick. So for this particular problem, each book has to be lifted up, except for the first one. The first one's already at the reference location. I'm going to go ahead and change my reference now to say this is h is equal to 0, right at the actual tabletop. Well, that work takes no work to put it into position. This one takes 17 times 0.045 meters. This one takes 17 times 0.090 meters. The idea is that each book is lifted a different amount. We're going to go ahead and call those H1, which isn't lifted at all, H2, where it's lifted 4.5 centimeters, H3 is lifted 9. We can write that sort of like so. Each height is a multiple of 4.5 centimeters, so each time I lift a book, I'm lifting it a different amount of height. Well, the way that I can compute this now is I can say that the GPE is just simply equal to, in this case here, so instead of me saying, I'm going to go ahead and write MGH here, but instead of having all of these things being the same height like they were up here in this problem, I'm going to go ahead and say that this is equal to 17 newtons, the weight of one book, and then multiplied by, in this case, I'm going to go ahead and add up all of these individual h's. I'm going to say the first one is 0, the second one is 1 times 4.5 centimeters. I'm going to go ahead and put that in as 0.045 meters, plus 2 times that, plus 3 times that, and so forth. And I need to do that for all of these books. So when I'm all said and done, what I get is 17. I'm going to go ahead and pull out a 0.045 out of that big sum. So 17 newtons. 0.045 is a common factor in every one of these terms. And so I'm just going to go ahead and pull that out. And what I'll get here is 0, plus 1, plus 2, plus 3, plus 4. And you can see based on my little summation over here that I have to go all the way to plus 5. And so now what I get is just a way of computing the total amount of gravitational potential energy, or in this case the total amount of work done to place all of those books into position. And in this case here, the 17 times 0.045 meters would be 0.765. And then I'm multiplying that by, let's see, that's 3, 6, 10, 15. And so when I'm all said and done, that amount of energy is about 11.5 joules, which with rounding we'd round that down to about 11 joules. And so the total amount of work done to stack those books would be 11 joules. And last but not least, I want to take a look at how we can use a little bit of trigonometry here to calculate an object's GPE if I choose a different reference location. Let's say that I'm really interested in saying what is the GPE of the wrecking ball at a location here if I choose this as my reference, so the position at its lowest point in the swing. And that would make sense based on how a wrecking ball is used. It has gravitational potential energy at this spot. As it swings down, it's going to be able to do work on a building or a wall or something along those lines down here. So this would make more sense to call this my reference. If it dropped down to the ground here, then I might say this is my reference location, but it makes more sense to call it up here. So in order for me to do that, I'm going to have to do a little bit of trig. I'm going to go ahead and think of this as as the ball at this position and the ball at this position. And in this case here, since this is 15 meters, I'm going to go ahead and say that that rope here is 15 meters. And this is 15 meters as well, so it'd be swinging along an arc, if you will. And since I told you that this was 25 degrees, what I'd be interested in is just knowing how high up they are above my reference. So I'm interested actually in this. This would be my H value. Well, for me to find that, what I'm going to do is I'm going to think of H is really 15 minus this. So if I can find this value, then I can find H. And H again is down here. So what you can see is that since this is a right triangle, this would be 15, this value right here, I'm going to use color coding here. This portion is actually 15 cosine 25. And again, that's just the hypotenuse multiplied by the cosine of that angle to get me that length. So H is actually, now H would just be equal to 15 minus 15 cosine 25. And that value is just a number that I can compute. So let's go ahead and get that quick. And that number looks to be about 1.4 meters. And so the object is really only 1.4 meters above the reference location for this particular example. So the gravitational potential energy it has at that position would just be 125 kilograms times 9.8 times 1.4, and that would be a way of calculating the GPE it has relative to the lowest spot. So in this case, that value would be about 1715 joules, and I could go ahead and write that with significant figures to just be about 1700 joules. And so again, way up top here, it may look like this thing's got a lot of gravitational potential energy, but that's only if I chose my ground as my reference, more than likely because it's swinging through here. this would make more sense to say it's got gravitational potential energy of 1700 joules relative to its lowest position that it would have during that swing. Okay, so your homework for gravitational potential energy problems will be these. Go ahead and give those a shot. Come to class with any questions. Go Bucks.